the immortal jellyfish. Every living thing on Earth, as far as we know, follows the same basic arc. It is born, it grows, it ages, and eventually it dies. That is the rule biology has held since the first single-celled organisms drifted in shallow water. Then there is Turritopsis dohrnii, a small, pale jellyfish, no bigger than a fingernail, that quietly refuses to play by the rule. Scientists have nicknamed it the immortal jellyfish, and the nickname is not really an exaggeration. When a normal jellyfish reaches old age, it falls apart, its tissues break down, its bell sags, and it is over. When the immortal jellyfish reaches that same point, or when it is injured or starved, it does something almost magical. The dying adult settles to the ocean floor, reabsorbs its tentacles, and rolls back its entire development. Its specialized cells revert to a younger, more flexible form. Within days, it has reorganized itself into a polyp, the juvenile stage every jellyfish passes through at the start of its life. From that polyp, a new adult eventually buds free. In effect, it has aged in reverse. Researchers in Italy first documented this trick in the late 1990s, and it has been confirmed many times since. There is no known limit to how often the cycle can repeat, which is why the word immortal slipped into the scientific literature. In the open ocean, of course, predators and disease still take their toll. Most immortal jellyfish do not actually live forever. They could, in theory. They simply rarely get the chance. If you ever needed proof that death is not as fundamental as it feels, a creature smaller than your fingernail has been quietly making the case for decades. The Methuselah Star. For a very long time, scientists agreed that nothing in the universe could be older than the universe itself. Then they found a star that seemed to break that rule. Catalogued as a quiet, faded object in the constellation Libra, it sits about 190 light-years from Earth, close enough to study in clear detail, which is exactly what made the problem so hard to ignore. Astronomers began calling it the Methuselah Star, after the longest-lived figure in the Hebrew Bible. The original measurements pointed to an age of around 16 billion years. Our universe itself is thought to be roughly 13.8 billion years old. That is not a small discrepancy. For a while, the simplest explanation was that something had to give, but no one knew what. Researchers spent years tightening every variable they could measure: the star's exact distance, its true brightness, the slow nuclear burning in its core, and the trace heavier elements scattered through its outer layers. Each refinement brought the age down a little. The newest figures, drawn from observations by the Hubble Space Telescope, and more recent refinements, place the Methuselah Star somewhere around 14 billion years old, with an uncertainty wide enough that it finally fits inside the age of the universe. That cosmic crisis is over, but the star remains astonishing. It formed in the very first generation of stars, possibly only a few 100 million years after the Big Bang, which means it has been quietly burning for almost the entire history of everything that exists. When you look up at the right patch of sky in Libra, you can find it with a modest telescope. A single faint dot, drifting in the dark, that has watched galaxies form and fade. Whatever else we ever discover, we know this much. Something out there has been here almost from the start. Tardigrades. Most people imagine that any creature small enough to live between grains of sand or on a fleck of moss would be among the most fragile life on Earth. Tardigrades, also known as water bears, calmly break that intuition. They are microscopic, eight-legged animals, barely the size of a grain of salt, and they may be the toughest organisms ever discovered. Researchers have boiled them, frozen them, dehydrated them for years, blasted them with radiation, and even sent them into the vacuum of outer space, and a stubborn fraction of them keep waking up. The trick is a survival state called cryptobiosis. When conditions turn hostile, a tardigrade pulls in its legs, expels almost all the water inside its body, and curls into a tiny dry barrel called a tun. In that state, its metabolism drops to less than 1% of normal. The animal is not dead, but it is not really alive either. It is simply waiting. Researchers have revived tardigrades that spent more than 30 years in this dried-out form, plumping back to active life within hours of being placed in water. What truly amazed scientists was the experiment in 2007, when European researchers strapped tardigrades to the outside of a satellite and exposed them directly to the radiation, vacuum, and freezing temperatures of low Earth orbit. Many of them survived, and some of the females even laid healthy eggs once they returned. No other animal has ever pulled off that trick. It is one thing to survive a desert. It is another to survive outer space without a suit. Tardigrades are quietly everywhere, in your garden, on rooftops, in mountain lakes, under polar ice. They are not powerful or fierce. They simply outlast almost everything else, which is its own quiet kind of victory. Damascus Steel. It is very common to hear that modern technology has surpassed everything ancient hands could make. For most things, that is true. There is one exception that still embarrasses metallurgists, and it is a sword. From roughly the 3rd century onward, smiths working with steel ingots imported from South Asia forged blades that became legendary across the medieval world. Crusaders called the metal Damascus Steel after the city where it was often traded. These blades held an edge for a remarkably long time, flexed without breaking, and carried a flowing, watery pattern on the surface that no other steel could reproduce. Then, around the 1700s, the recipe vanished. The original ore source in India ran out, the trade routes shifted, and the last smiths who knew the technique died without writing it down. By the time chemists and historians thought to ask, no one alive could make a true Damascus blade. Modern smiths have produced steels that look similar, called pattern-welded steel, but the internal structure is not the same. In the early 2000s, materials scientists used powerful electron microscopes on genuine Damascus blade samples and made an unexpected discovery. The steel contained carbon nanotubes and tiny wires of iron carbide, structures so small that no one in the ancient world could have known they were there. These hidden features helped give the blades their flexibility and a famously enduring edge. The smiths almost certainly stumbled into the recipe through trial and error, working with a specific ore from India called Boötes, and producing nanomaterials without any idea what they were doing. A craft so refined that it accidentally invented nanotechnology, then quietly disappeared. The blades that survive in museums are still sharper than most modern knives, hammered out by hands that never knew what they had created. The Great Attractor. When we picture the universe, we tend to imagine galaxies drifting outward in every direction, calmly carried along by the expansion of space. That picture is mostly right. There is one strange exception sitting roughly 250 million light-years from Earth, and the more we learn about it, the stranger it gets. Astronomers call it the Great Attractor, and it is tugging our entire galaxy, along with thousands of others, toward a single point in space. The first hint came in the late 1970s, when researchers noticed that our local group of galaxies was not moving the way pure cosmic expansion predicted. Something was pulling us off course at roughly 600 kilometers per second, a velocity that demanded an enormous invisible mass somewhere in front of us. The trouble was, that direction lay behind the brightest part of the Milky Way, a region astronomers call the zone of avoidance. Our own galaxy was, in effect, blocking the view. Slowly, using radio waves and infrared light that can pierce the dust, observers began to piece the answer together. The Great Attractor turned out to be a vast concentration of galaxies and dark matter, anchored by a structure called the Norma Cluster. Even that, it later emerged, is just a foothill. The true gravitational center sits much deeper, in a much larger supercluster called the Shapley concentration, a structure so massive that everything for hundreds of millions of light years bends toward it. Right now, you are drifting toward the Great Attractor at a speed of millions of miles per day. The universe is expanding around you, and yet a piece of it, somewhere in the dark behind a familiar constellation, is quietly winning the tug of war. None of us will arrive in any human lifetime. The pull, however, never stops. The platypus. When the first stuffed platypus arrived in London in 1799, British scientists were convinced they were looking at a hoax. It had the body of a furry brown mammal, a flat duck-like bill where the mouth should be, a wide flat beaver paddle for a tail, and webbed feet. A naturalist named George Shaw reportedly took a pair of scissors to the specimen, certain that someone in Asia had sewn together pieces of different animals to fool him. The platypus survived its first review, though, and has been quietly embarrassing biology ever since. Field studies in Australia eventually confirmed the platypus is exactly what it appears to be. It is a mammal that lays eggs, which by every textbook rule should not happen. It has no teeth and uses gravel in a pouch in its mouth to grind food. The males carry a venomous spur on each hind ankle, painful enough to bring a grown human to their knees. Females do not have nipples, instead sweating milk through patches on their skin so the babies can lap it up. Then came the truly strange discovery. The platypus is electroreceptive. Tiny sensors in the duck-like bill can detect the faint electric fields given off by the muscles of shrimp and worms in muddy river water. When a platypus dives, it actually closes its eyes, ears, and nose, and hunts entirely by reading the electricity of life around it. In 2008, geneticists sequenced its full genome and found a creature that carries traits of mammals, reptiles, and birds, all blended into a single living animal. The platypus is not really a missing link. It is more like a snapshot of a path that evolution stopped exploring almost everywhere else. The branch survived in one quiet river system, where it still does not care what the textbook says. The wow signal. On the night of August 15th, 1977, a single piece of paper started a mystery that has never been solved. An astronomer named Jerry Amon was reviewing computer printouts from the Big Ear radio telescope at Ohio State University when his eyes snagged on a column of letters and numbers far above the usual noise. The intensity was so striking that he circled the entire run in red ink and wrote a single word in the margin. Wow. That signal had arrived on a frequency known as the hydrogen line, a frequency astronomers had long considered the most likely choice for any intelligent species trying to contact others. It came from the direction of the constellation Sagittarius, lasted exactly as long as the telescope's field of view would have allowed a fixed source to drift through, and showed no sign of human origin. No satellite was passing overhead. No earthbound transmitter could explain it. For 72 seconds, something far out in space had spoken. Astronomers have been listening to that same patch of sky ever since. Hundreds of searchers with newer, more sensitive instruments have heard absolutely nothing. The signal has never repeated. Various natural causes have been proposed over the years, including a passing comet, but every explanation has problems, and none of them has been confirmed. Whatever happened that summer night remains the strongest unexplained signal in the entire history of the search for intelligent life. It does not prove that anyone is out there. It does not prove that anyone is not. It simply hangs in the historical record, a single tantalizing exhibit, waiting for a second chance that may never come. Almost 5 decades on, the wow signal is still listening for an answer of its own. Axolotl Regeneration. In a fading set of canals on the outskirts of Mexico City lives one of the most extraordinary animals on Earth, and almost no one outside of biology has heard of it. The axolotl is a salamander that never quite grows up. It keeps its feathery pink external gills, its tail fin, and its underwater life for its entire span. Its face seems to be permanently smiling. Tiny black points serve as eyes. Underneath that gentle appearance, the axolotl quietly does something that medical science still cannot fully explain. If you remove one of its legs, the axolotl simply grows a new one. The wound does not even scar. Within weeks, a perfect replacement leg, complete with bone, muscle, and nerves, has formed where the original used to be. The same trick works for parts of the heart, parts of the spinal cord, sections of the jaw, segments of the lungs, and even portions of the brain. Other animals heal. The axolotl rebuilds. Researchers around the world have spent decades trying to understand how. Some of the answer lies in clusters called blastema cells that gather at the wound site and behave almost like the early cells of an embryo. They listen to chemical signals from the surrounding tissue and rebuild exactly the right structure, in exactly the right place, at exactly the right size. Human bodies have lost most of this ability somewhere deep in evolutionary time. In a strange twist, the axolotl is now critically endangered in the wild, even as it thrives in laboratories and aquariums all over the world. The hope of stem cell research, of repaired spinal cords, of regrown organs, all of it may one day owe a serious debt to a little smiling salamander that, against every odd, refused to grow up. Greek fire. For roughly 500 years, the Byzantine Empire was protected by a weapon so terrifying that enemies sometimes surrendered at the sight of the ships carrying it. The recipe was called Greek fire. It was a sticky liquid that could be sprayed from a bronze siphon at the front of a warship, ignite in mid-air, and continue burning even on the surface of the sea. Water did not extinguish it. Sand barely slowed it. Wooden enemy fleets simply melted into the Aegean. The Byzantines guarded the formula so carefully that only a small group of family members and trusted engineers ever learned how to make it. Different stages of the recipe were assembled in different workshops by different specialists so that no single person could betray the whole. The pumps and pressure vessels needed to deliver the fire were also tightly controlled. Capturing a Byzantine warship intact and learning the secret became the dream of every rival admiral, and as far as we know, none of them ever managed it. When the empire fell, the formula fell with it. Modern historians and chemists have tried to reconstruct Greek fire from fragmentary descriptions in old chronicles. Most agree it contained refined petroleum from natural surface seeps around the Black Sea, mixed with resins and possibly quicklime to give it the property of igniting on contact with water. Exact proportions remain a guess. This weapon held off Arab fleets, Bulgarian raids, and Slavic incursions, buying Constantinople centuries that might otherwise have been measured in decades. It may be the only military technology in history that helped save an empire and then died with it, leaving only smoke in the historical record and a recipe no one can quite finish. Ball lightning. If you ever needed proof that nature still has unsolved tricks left for science, consider ball lightning. For at least 2,000 years, people have reported seeing glowing spheres about the size of an orange or a grapefruit, drifting slowly through the air, sometimes during thunderstorms, sometimes inside houses, sometimes through closed windows without breaking the glass. They float, they hiss, and after a few seconds or a few minutes they vanish, occasionally with a small bang. Witnesses include sailors, airline pilots, kings, and the occasional nervous physicist. For most of recorded history, scientists dismissed ball lightning as a misperception, an illusion, or a lie. Then, in 2012, a research team in China happened to point a high-speed camera and a spectrograph at the right patch of ground during a thunderstorm. A normal lightning strike was caught on film, and immediately afterward, a glowing ball drifted out of the soil and lingered for almost 2 seconds before fading. The team recorded its light spectrum, which showed traces of silicon, iron, and calcium, exactly the elements you would expect in vaporized dirt. That single recording has not closed the case. Different events around the world look subtly different, and laboratory attempts to reproduce ball lightning have only succeeded a few times under very specific conditions. Some researchers think it is plasma. Some think it is a slow-burning aerosol. Some think more than one phenomenon is hiding under the same name. What seems certain is that the eyewitness reports were not all imagination. Something is happening in the sky and inside houses during certain storms. It is rare, it is brief, and almost 2,000 years after the first written description, we still do not really know what it is. The Bombardier Beetle. Imagine a creature so small you could mistake it for a speck of dirt on a leaf, yet armed with a chemical weapon so precise that early biologists thought it had to be a folk tale. That is the Bombardier Beetle, roughly an inch long, found on every continent except Antarctica. This unassuming insect carries inside its body the makings of a small, focused explosion. When threatened, it fires a boiling jet of toxic spray out of its abdomen, aimed with remarkable accuracy at whatever is bothering it. Inside the beetle are 2 separate chambers. One holds a chemical called hydroquinone. Another holds hydrogen peroxide. Each on its own is fairly inert. When the beetle is alarmed, valves open and the 2 chemicals flow together into a tough reaction chamber lined with enzymes. The mixture instantly heats to about 100 degrees Celsius, the temperature of boiling water, and erupts out of a swiveling nozzle at the rear of the abdomen. The spray comes in rapid pulses, almost like the cycling of a tiny pulse jet engine. For decades, biologists struggled to figure out how such a precise system could have evolved by gradual steps. Each individual component looks like it would need to be in place all at once, or it would be useless or fatal. Patient research has now reconstructed plausible intermediate stages in beetle ancestors, where the same chemicals served simpler defensive roles. The full system is breathtaking, but it was assembled piece by patient piece. Engineers studying jet propulsion have looked closely at the Bombardier Beetle for ideas. A creature smaller than a fingernail, building, storing, and aiming a controlled explosion, all without melting itself, is a feat of natural engineering that humans are only beginning to match. Magnetars, out beyond our solar system, scattered through the Milky Way, sit perhaps a few dozen objects so absurdly extreme that, when astronomers first proposed them, the idea was nearly dismissed. They are called magnetars. Each one is the leftover core of a giant star that exploded, compressed into a ball about 12 miles across, weighing more than the sun. What makes them special is the magnetic field. which is so strong that the laws of physics in their vicinity stop behaving the way we are used to. A typical magnetar has a magnetic field roughly 1,000 trillion times stronger than the Earth's. To put that in human terms, if you were unfortunate enough to find yourself within 1,000 kilometers of one, the magnetic force would distort the very atoms in your body. Bonds would stretch. Chemistry would simply stop working. Your form would be unmade well before you got close enough to feel anything else. Magnetars announce themselves by occasionally cracking. The crust of one of these stars is a kind of rigid crystal lattice, and when the stresses inside the body shift, the crust fractures. A single starquake can release more energy in 1/10 of a second than the sun gives off in 100,000 years. In 2004, a magnetar more than 50,000 light-years away briefly outshone the full moon in gamma rays, disturbing the upper atmosphere of Earth despite the immense distance. Despite all that ferocity, magnetars cool quickly and fade. Most of them remain active for only a few tens of thousands of years before settling into silence. While they last, however, they are among the most violent, beautiful, and absurd objects in the known universe, quietly explaining away physics problems we used to think were unsolvable. Stradivarius Violins. Sometime in the late 1600s, in a small town in northern Italy, a craftsman named Antonio Stradivari began making violins that the world has been chasing ever since. He turned out roughly 1,100 instruments during his long lifetime, and the few hundred that survive today are valued in the millions of dollars. Professional musicians describe their sound with words like singing, alive, almost human. For more than 3 centuries, no one has managed to consistently match them. Modern violin makers, equipped with computer modeling and laser scans of the originals, can build instruments that match a Stradivarius in shape down to fractions of a millimeter. They still sound different. Various theories have tried to explain the gap. Some researchers have pointed to the wood, harvested in an unusually cold stretch of European weather called the Maunder Minimum, when trees grew slowly and produced denser, more uniform timber. Others have studied the varnish, the glue, the chemical baths Stradivari may have used to treat the wood. Blind listening tests have produced their own surprises. In several controlled studies, expert violinists, even sitting blindfolded in a concert hall, often could not reliably tell a modern instrument from a Stradivarius. In some tests, the modern violins were preferred. The mystique of the name does heavy lifting, but the instruments themselves remain genuinely exceptional in ways no one has quite pinned down. The deeper answer may be that there is no single trick. A Stradivarius is the product of a vanished craft tradition, a vanished climate, vanished suppliers, and a master with hundreds of small habits, learned by hand and never written down. 300 years later, a few hundred wooden boxes from a quiet Italian workshop still set the standard that the rest of the world is politely chasing. The Nazca Lines, high above a stretch of dry coastal desert in southern Peru, drawn into the gravel of the Nazca Plain, are hundreds of enormous figures. A hummingbird as long as 2 basketball courts, a monkey with a curling tail bigger than a football field, a spider, a whale, a tree, dozens of perfectly straight lines that run for miles across the plateau without bending. From the ground, the figures are nearly invisible. From the air, they become unmistakable. The strange part is, they were made roughly 2,000 years ago, long before anything resembling flight. The drawings were made by the Nazca people between about 200 BC and 600 AD. The technique is straightforward once you see it. Workers cleared away the dark, rust-coloured stones from the desert's surface, exposing the lighter sand beneath. Almost no rain falls on this plateau, so the lines simply stayed. What is harder to explain is the planning. Many figures are mathematically precise across distances far too great to take in from ground level. For a long time, the purpose of the geoglyphs was wildly debated. Early theories ranged from giant calendars to runways for visiting astronauts, which has been thoroughly debunked. The current consensus is far more grounded and far more interesting. Many of the lines align with sources of underground water, others with sacred mountains. Archaeologists believe the Nazca walked the figures in ritual processions, asking the land for rain. In 2024, new surveys using artificial intelligence to scan high-resolution drone imagery uncovered more than 300 previously unknown geoglyphs in a single year. The desert is still revealing them. A canvas the size of a small country, scratched by hand into the dirt, is still talking to anyone willing to listen. The Voynich Manuscript, sitting in the Rare Books Library at Yale University, is a small, illustrated book that has resisted every attempt to read it for more than 6 centuries. It is called the Voynich Manuscript, named for the antiquarian who bought it in 1912. The pages are covered in flowing, careful script, in an alphabet no one has ever identified, accompanied by paintings of plants that match nothing in the botanical record. Naked women bathing in green pools connected by strange plumbing, and circular charts that look like astronomy but obey no known sky. Carbon dating has established that the parchment was made in the early 1400s, somewhere in Central Europe. The ink is consistent with that period. The book is not a modern hoax. It is a real, painstakingly produced document with neat paragraphs, headings, and a careful illustrator who used the same colours throughout. Whoever made it spent an enormous amount of time and money on it. For more than 100 years, the world's best codebreakers have tried to crack the writing. The team that broke the German Enigma cipher tried, including the famous American cryptanalyst William Friedman. The team that broke Japanese naval codes tried. So have linguists, historians, computer scientists, hobbyists, and, more recently, machine learning models. Letters cluster in statistically natural ways, suggesting a real language, yet no proposed translation has held up to scrutiny. Claims that it is Hebrew, Aztec, an early form of Turkish, or simply a clever fake all surface and fade. Whatever it is, someone in medieval Europe produced a complete book in an unknown script about an unknown world and spent serious money to do it. The Voynich Manuscript may be a hoax that fooled even its author. It may be the last surviving copy of a forgotten knowledge. So far, it is simply quiet. Sailing stones. In the cracked, parched basin of Racetrack Playa in Death Valley, there are stones that move. They are not small. Some weigh more than a grown adult. Visitors walking the dry lakebed find long, curving trails carved into the mud, sometimes hundreds of feet long, often ending at an innocent stone sitting at the tip of its own track. For decades, no one could quite explain how something that heavy travelled so far across flat ground that no human had ever seen in motion. The trails were too clear to be a hoax. Curving paths, sudden right-angle turns, parallel grooves cut by neighbouring stones, theories piled up over the years. Strong winds, hurricane gusts, freezing slicks of ice, even magnetic fields and pranksters were all proposed at one point or another, and each idea ran into some inconvenient detail. The stones moved when no one was watching, on days when there was almost no wind, on a surface as level as a kitchen counter. The puzzle was finally solved in 2014. A pair of geologists named Richard Norris and James Norris set up time-lapse cameras and GPS units on a selection of the stones and waited. The mystery turned out to require a quiet collaboration between thin sheets of overnight ice, a shallow film of meltwater, and a light afternoon breeze. As the ice broke up into floating panels, it gripped the stones and pushed them along the slick mud at a gentle walking pace, slow enough that you could blink and miss it. Once the conditions ended, the ice melted away and the water dried, leaving only the tracks and the stones, looking exactly as if they had walked themselves into place. Nature solved the puzzle with patience and weather, the same way it solves most of its quieter mysteries. Blood Falls, Antarctica. When an Australian geologist first reported in 1911 that a glacier in Antarctica was bleeding a thick red stream onto the ice, almost no one believed him. The image was too strange. Pure white ice, a frozen continent at the bottom of the world, and a slow waterfall of what looked like blood pouring from the snout of a glacier in the Taylor Valley. The phenomenon was named Blood Falls, and for more than 100 years, it has refused to fit any simple explanation. The first guesses involved red algae, the kind that sometimes tints alpine snow pink in summer. Closer study ruled that out. The water was far too cold and far too dark, deep inside a glacier where no light penetrates. Chemists who carefully sampled the seeping liquid found it was extremely salty, far too salty to freeze even at the bitter Antarctic temperatures. They also found it was rich in iron. When that iron met the open air, it rusted, the same chemistry that turns blood and old metal the same dark crimson. The deeper story took another century to piece together. Beneath the Taylor Glacier sits a sealed lake of ancient water, trapped for somewhere between 1 and 2 million years. That hidden pool is fed by no sunlight, no oxygen from the air, and yet it contains a thriving community of microbes. They survive by feeding on the iron and sulfur compounds dissolved in the water, the way some life clings on near deep sea vents. When the pressure inside this buried lake finds a crack in the glacier, a slow plume reaches the surface. What pours out of the ice is salt, iron, and the breath of life that has been hiding from the sun longer than humans have existed. The Antarctic, it turns out, is not as empty as it looks. Oumuamua. On October 19, 2017, a telescope in Hawaii caught a faint dot moving fast through the inner solar system. Within hours, it became clear that this dot was not orbiting the sun the way a comet or an asteroid would. It had come in from interstellar space, swung past the sun once, and was already on its way back out. Astronomers named the visitor Oumuamua, a Hawaiian word that roughly translates as a scout or a messenger arriving from far away. The object refused to behave. Its brightness varied wildly as it tumbled, suggesting an extreme shape, perhaps a long thin cigar or a flat pancake stretched maybe 1/3 of a mile in its longest dimension. It was reddish, dry, and apparently empty of the puffy cloud of gas that follows any normal comet near the sun. Yet when researchers tracked its path carefully, they found a tiny extra push that gravity alone could not explain. Something was nudging it away from the sun, almost like the slow exhaust of an unseen engine. Most astronomers eventually settled on the idea that Oumuamua was a fragment of a frozen, exotic ice from a distant star system, perhaps mostly nitrogen or hydrogen, slowly evaporating in the warmth of our sun and producing the small thrust. A few scientists, most notably Avi Loeb at Harvard, argued that the extra push and the unusual shape were better explained by a thin, artificial sail of unknown origin. The debate has not been settled and almost certainly will not be. By the time we noticed Oumuamua, it was already leaving. Within a few months, it was too dim to follow. Whatever it was, our solar system was its briefest stop on a journey that began somewhere we cannot see, and continues towards somewhere we will never reach. Hoag's object. In 1950, an American astronomer named Arthur Hoag was scanning photographic plates of the sky when he spotted something he had never seen before. It looked like two galaxies, one nested perfectly inside the other, separated by a clean dark ring of empty space. At first, Hoag suspected it was a trick of the camera, perhaps a gravitational lens bending the light of one galaxy into a ring around another. Closer investigation ruled that out. He was looking at a single object, and that object had no business existing. Hoag's object, as it came to be called, sits about 600 million light-years from Earth. At its core is a tight, almost spherical cloud of older yellow stars, roughly the size of a small galaxy in its own right. Around that core, separated by a startlingly clean gap, runs a ring of younger blue stars laced with bright nests of star formation. There are no spiral arms, no obvious bridge between the inner ball and the outer ring. The whole thing is held together by gravity, but how it arrived in this shape is still being debated. The leading idea is that sometime in the deep past, a smaller galaxy plunged straight through the center of a larger one. The collision sent a wave of compression rippling outward, triggering starbirth in a perfect circle, while leaving the original core mostly intact. Other theories involve unusual rotation patterns or strange interactions with dark matter. None of them is fully proven. Through a small telescope at the right exposure, even amateur astronomers can capture an image of Hoag's object. A pristine ring of light around a quiet golden core, drifting in deep space, with a tiny second ring galaxy visible through the gap. It is a reminder that the universe is perfectly happy to build shapes we would have called impossible. The Oklo Natural Nuclear Reactor. 2 billion years ago, deep in what is now the West African country of Gabon, a strange pocket of buried rock began to do something that should have been impossible without humans, an industrial economy, and a careful team of physicists. It started a nuclear chain reaction. Over the next few 100,000 years, that pocket of uranium ore quietly produced electric heat, split atoms, and powered itself, all without any conscious help. The site is now called the Oklo Natural Nuclear Reactor, and it is the only known example of nature ever managing this trick. The discovery came in 1972, when French chemists processing uranium from the Oklo mine noticed that the ore contained slightly less of the rare fissile isotope known as uranium-235 than it should have. The deficit was tiny, but it was real. Detailed analysis of the surrounding minerals turned up the unmistakable fingerprints of fission products, including specific isotopes of neodymium and xenon that only appear after a nuclear reaction has occurred. For a brief geological window, conditions in the Oklo deposit had aligned perfectly. The uranium was rich enough in the fissile isotope because radioactive decay had not yet thinned it out, and groundwater seeping through the ore acted as a natural moderator, slowing neutrons enough to keep the reaction going. The reactor likely ran in pulses, heating up, boiling away the water, shutting down, cooling, and starting again, roughly every few hours for several 100,000 years. The total energy released was modest by industrial standards, perhaps the equivalent of a single small power plant running for a few decades. The deeper lesson, though, is humbling. Without inventing a thing, the planet quietly built and operated a working nuclear reactor long before any animal walked the Earth. Quasicrystals. For most of the 20th century, every crystal known to science obeyed a strict rule. The atoms inside any solid crystal had to be arranged in patterns that repeat in regular intervals, and the symmetry of that pattern had to follow specific allowed shapes. Five-fold symmetry, the kind you see in a pentagon or a starfish, was simply forbidden. You could not tile a flat surface with five-sided shapes without gaps. The same was thought to be true at the atomic level. In April of 1982, an Israeli materials scientist named Daniel Shechtman cooled a melted alloy of aluminum and manganese and pointed an electron microscope at it. The diffraction pattern that appeared on his screen was clean, sharp, and unmistakable. It showed perfect five-fold symmetry. He wrote 3 question marks in his notebook. When he announced the result, the chemistry community pushed back hard. The famous double Nobel laureate Linus Pauling reportedly said there were no quasicrystals, only quasiscientists. Shechtman held his ground. Other labs reproduced the result. New materials with even more impossible symmetries followed: 6-fold, 10-fold, 12-fold. Mathematicians realized that these crystals had a structure that does not repeat in the ordinary sense, yet still produces a sharp pattern. They are now called quasicrystals. The atomic arrangement is ordered, but never quite the same twice, like a tiling pattern proposed years earlier by Roger Penrose. In 2011, almost 3 decades after his discovery, Shechtman received the Nobel Prize in Chemistry. Quasicrystals have since been found inside meteorites, formed under enormous shock pressure, and in industrial coatings that resist sticking and corrosion. A whole class of solid matter that almost everyone agreed could not exist was hiding in plain sight, waiting for someone stubborn enough to take a closer look. Time crystals. An ordinary crystal, like a grain of salt or a snowflake, repeats its atomic pattern across space. Each unit of structure lines up next to the next one in a quiet, regular grid. In 2012, the Nobel-winning physicist Frank Wilczek asked a question no one had thought to ask before. If matter can repeat itself across space, why can it not also repeat itself across time? He named the hypothetical version a time crystal. The idea sounded like science fiction. The trouble was that, for a time crystal to be real, its atoms would have to keep moving forever in a synchronized way, without consuming any energy, without ever winding down. That looked uncomfortably close to a perpetual motion machine, which the laws of thermodynamics explicitly forbid. For years, debate raged over whether such a thing could even exist. Then physicists realized you could not build a time crystal in true equilibrium. You could, however, build one in a carefully isolated, driven system where the matter still settled into a stable rhythm of its own. In 2017, 2 separate teams pulled it off. One group used a chain of trapped ions at the University of Maryland. Another group used defects inside a diamond at Harvard. Both setups, when nudged, fell into a steady oscillation at a beat that did not match the input, behaving exactly as Wilczek had predicted. More recent experiments have produced time crystals on quantum computers, where their behavior can be examined in clean, isolated detail. What this all means in practical terms is still being worked out. Quantum computers, ultra-precise clocks, and new kinds of memory have all been suggested as potential applications. The deeper surprise is simpler. A phase of matter that breaks the symmetry of time itself, treated as fantasy a decade ago, now sits patiently inside actual laboratory equipment, keeping its own steady beat. Superfluid helium. Some substances behave nothing like the liquids and gases we are used to. Cool the element helium down close to the coldest temperature physics allows, just 2 degrees above absolute zero, and it stops acting like a normal fluid. It becomes what physicists call a superfluid. The transition is sharp. One moment you have an ordinary cold liquid sitting in a beaker, a fraction of a degree colder, and that liquid is doing things no other substance does. Pour superfluid helium into a small open cup, and a thin film of it will quietly creep up the inside wall, over the rim, and down the outside surface, drip by drip, until the cup is empty. Stir the liquid, and the swirl will continue spinning, without slowing, for what is effectively forever in human terms. Drop a small object into it, and the object can move through the fluid with zero drag. Friction, as we usually understand it, simply stops existing. The reason is purely quantum mechanical. At low enough temperatures, a large fraction of the helium atoms slip into the same quantum state and start behaving as a single coordinated wave. Many of the rules that hold for everyday liquids depend on countless tiny random interactions between particles. In a superfluid, those interactions are silenced. The whole pool of liquid moves with one mind, slipping through the smallest cracks and climbing surfaces that no ordinary fluid could climb. The discovery, made in 1937 by Piotr Kapitsa and independently by John Allen and Don Missener, eventually earned Kapitsa a Nobel Prize. Beyond the strangeness, superfluid helium is now used in extremely sensitive instruments, including the cooling systems for some particle accelerators and certain high-resolution telescopes. The universe, it turns out, allows a state of matter that quietly defies the friction we take for granted. Quantum tunneling. Walls seem solid. Toss a ball at a wall, and it bounces back every time. The intuition that solid objects stop other objects is so deeply hardwired into us that it feels like a law of nature. At the level of atoms and electrons, though, that intuition quietly collapses. Quantum particles, given a barrier they should not be able to cross, sometimes simply appear on the other side, as if the barrier were not there. The phenomenon is called quantum tunneling, and it underwrites a surprising amount of how the universe actually works. The trick comes from the strange fact that quantum particles do not have one fixed location. They have a wave-like spread of possible positions, smeared out across a region of space. When that wave encounters a barrier of energy, most of it bounces back, but a small piece of the wave can extend into the barrier and out the other side. There is a real probability that the particle, when next measured, will be sitting beyond an obstacle it would never have had enough energy to climb. Tunneling is not just a laboratory curiosity. It runs the sun. Hydrogen nuclei in the core of every star do not, strictly speaking, carry enough energy to overcome their mutual electric repulsion. Without tunneling, fusion would not happen, and the sun would have stayed dark. The same effect makes possible the alpha decay of heavy atoms, the operation of certain semiconductor diodes, and the impossibly small features on modern computer chips, where electrons routinely sneak across insulating layers a few atoms thick. For decades, physicists assumed the tunneling event itself was instantaneous. Recent experiments suggest the particle does take a tiny but measurable amount of time on the other side. The wall is not really a wall. It is a probability, and the universe is calmly comfortable with that. Neutron star mergers created Earth's gold. Every wedding ring, every gold tooth, every electronic contact in every phone, every grain of gold ever dug out of the Earth came from somewhere violent. For a long time, astronomers assumed it had been forged inside ordinary exploding stars. The problem was the numbers. Conventional supernovas can produce light elements and a respectable amount of iron, but the calculations never quite worked out for the truly heavy metals. There simply was not enough cosmic violence to account for the gold, platinum, and uranium scattered through the rocks beneath our feet. The answer arrived in a single spectacular event in August of 2017. detectors on Earth picked up gravitational waves, ripples in space itself, coming from a galaxy about 130 million light-years away. Less than 2 seconds later, satellites caught a burst of gamma rays from the same patch of sky. Telescopes scrambled to look. Within hours, observatories all over the world saw the afterglow of 2 neutron stars spiraling into each other and merging. The event was named GW 170817. The light from the collision faded in a very specific way over the next few days. Spectroscopy revealed the signatures of heavy elements being born and decaying in the expanding debris. Astronomers estimated that this single merger had produced something like 10 Earth masses worth of gold and platinum, plus uranium, lead, and other heavy metals, scattering across the galaxy at near the speed of light. The implication is quietly extraordinary. Almost every atom of gold on Earth, including the gold in any ring you might be wearing, formed billions of years ago in the violent kiss of 2 dead stars. The metal then drifted for billions of years more until a cloud of dust and debris collapsed into our solar system. Wedding rings, it turns out, are recycled stardust. Slime mold. If you handed a biologist a single-celled organism with no brain, no nerves, and no eyes, and asked them to design an intelligence test it would pass, they would probably laugh. Then slime mold quietly began passing every test anyway. Slime mold is not a plant, not an animal, and not really a fungus, though it was filed under fungi for a long time. The bright yellow species called Physarum polycephalum is the celebrity of the family, a spreading sheet of slow, syrupy yellow living tissue that creeps across damp logs in forests around the world. Around the year 2000, a Japanese researcher named Toshiyuki Nakagaki placed a chunk of Physarum at one end of a small maze and a flake of oatmeal at the other. The slime mold spread out in every direction, then steadily withdrew from the dead ends, leaving a single connecting strand along the shortest path between itself and the food. With no neurons in sight, it had solved a maze. Later experiments only made the slime mold stranger. Set out flakes of oatmeal in the geographic pattern of cities around Tokyo, and Physarum knits a transport network between them that closely mirrors the actual layout of the real Tokyo rail system. Place it under fluctuating temperatures, and it begins to anticipate the next change before the next cycle arrives. Cut a piece off, fuse it with a different slime mold, and the memories of routes through pipes appear to transfer. What slime mold has in place of a brain is a vast network of chemical signals that travel through its single gigantic cell. Out of that simple system grows behavior we usually associate with thinking. The lesson is not that slime molds are smart in the human sense. It is that intelligence is older, stranger, and far more widely distributed than we tend to imagine. HeLa Cells. In a segregated ward of Johns Hopkins Hospital in 1951, a young black woman named Henrietta Lacks was being treated for an aggressive cervical cancer. Without telling her or her family, doctors took a sample of her tumour. They handed it to a researcher named George Gay, who was trying, mostly without success, to grow human cells in a laboratory. Cells from previous patients had always weakened and died within a few days. The cells in this new sample did something different. They grew and refused to stop. Henrietta Lacks died of her cancer that October at the age of 31. Her cells, however, are still alive today, in laboratories all over the world. They were named HeLa Cells, after the first 2 letters of her first and last names. Scientists eventually realized that her tumour carried a particular set of genetic changes that made her cells effectively immortal in culture. Given food and warmth, They double roughly every 24 hours, indefinitely. The total weight of HeLa cells grown since 1951 is estimated, by some researchers, at more than 50 million metric tons, enough to circle the Earth several times if you laid the cells end to end. They have been used to test the polio vaccine, to study cancer and AIDS, to map the effects of radiation, to investigate how viruses infect human tissue, and to develop countless modern medicines. Her cells have even flown to space to see how human tissue responds to microgravity. For decades, the Lax family knew nothing of the experiments. The ethical, racial, and consent issues raised by her case helped reshape modern medical research. Today, her descendants are part of the decision-making around her cells, and a measure of justice has begun to catch up. Henrietta Lacks did not live a long life, but biologically, a part of her may never die. Acquired savant syndrome. There are people walking around today who can solve enormous mathematical puzzles in their heads, sketch entire city skylines from a single helicopter ride, or play complex piano pieces by ear, and who could not do any of those things until a serious head injury changed their brain. Their condition is called acquired savant syndrome. It is rare, fewer than 100 well-documented cases worldwide, but each one quietly suggests that hidden abilities may lie buried in every human brain. One of the most studied cases is a man named Jason Paget. In 2002, he was assaulted outside a karaoke bar and struck in the head. After the attack, he began to see the world differently. Patterns of fractal geometry seemed to lie over every surface: water, leaves, light through windows. He had no advanced math background. Without instruction, he started teaching himself trigonometry and complex geometry, eventually producing hand-drawn fractal diagrams that mathematicians around the world have studied. Another case, a man named Derek Amato dove into a shallow pool, struck his head, and recovered with a severe concussion. Within weeks, he sat down at a piano he had never seriously played and began composing intricate music. The notes seemed, in his own description, to scroll in front of his eyes. Brain scans of acquired savants often show unusual patterns in the left hemisphere, where damage may release the right brain's pattern recognition from its usual constraints. What this all suggests is that the human brain holds powers most of us never see. The cost is steep, often a serious injury, sometimes lasting cognitive or emotional difficulty, and the trade is not one anyone would choose. Yet the existence of these people argues that talent is not always something added from the outside. Sometimes it is something that was always there, finally let out. Synesthesia. Some people read the word Tuesday and see the colour yellow. Some people hear the note F sharp and taste lemon. Some people, glancing at a number printed on a page, instinctively know it is gentle, or angry, or warm. Their senses run together in ways that, to anyone else, sound impossible. The phenomenon is called synesthesia, from a pair of Greek words meaning together and sensation. It is not a disease, not a defect, and not particularly rare. By careful estimates, around 4% of the population has some form of it. The most common version is grapheme color synesthesia, in which letters and numerals carry consistent colors. The letter A might always be red, the number 5 always green. Variants include sound color synesthesia, in which music or noises produce visible color patterns, taste shape synesthesia, in which flavors come with associated forms, and ordinal personification, in which days of the week or numbers feel like distinct personalities, with moods. Researchers using brain scans have found that, in synesthetes, the neighboring brain regions responsible for different senses are unusually well connected. Signals that normally stay in one lane spill quietly into the next. Genetics plays a role. The trait often runs in families. Famous synesthetes include the composer Olivier Messiaen, the painter Wassily Kandinsky, and the physicist Richard Feynman, who reported seeing equations in vivid color long before he could explain why. Far from being a problem, synesthesia often helps memory and creativity. Words attached to colors are easier to recall. Music tied to shapes can suggest new compositions. To synesthetes, the rest of the world seems oddly muted, as if everyone else were listening to a podcast in monochrome. To everyone else, synesthesia is a quiet reminder that perception is more flexible than it feels. Fetal microchimerism. After every pregnancy, the mother and the child go their separate ways, or at least that is what people have always assumed. Modern biology has quietly revealed something stranger. During pregnancy, a small number of cells from the developing baby cross the placenta and lodge in the mother's body. They do not always leave. The phenomenon is called fetal microchimerism, and it means that almost every woman who has ever been pregnant carries traces of her children inside her tissues, sometimes for the rest of her life. The first hints arrived in the 1970s, when researchers discovered male cells circulating in the blood of women who had given birth to sons. Since male cells are easy to identify by their Y chromosome, they were the easiest to track. Over the decades, the picture grew. Fetal cells have since been found in maternal bone marrow, in skin, in the thyroid, in the liver, and most strikingly, in the brain. Some of these cells, decades after the pregnancy ended, are still alive and active. What they are doing there is one of the most fascinating questions in modern biology. In some cases, fetal cells appear to help the mother heal, gathering at sites of injury and behaving almost like personal stem cells. In other cases, they have been associated with autoimmune conditions, as if the mother's body had begun reacting to the lingering presence. The picture is still being sorted out. The outcomes seem to depend on the mother, the child, and 1,000 details no one fully understands yet. The result is a quiet, biological intimacy that no story really captures. A mother is not simply someone who carried a child for 9 months. She is, in a measurable sense, partly built of the children she carried, walking around with their cells for decades, neither alone nor quite the same person she was before. Phantom limb pain. People who have lost an arm or a leg often report that the missing part is still there. They can feel its weight, its position, the itch on the back of a hand they no longer have. Sometimes the sensations are mild and fleeting. Sometimes they are agonizing, a crushing pain in fingers that no longer exist, or a hand frozen in a clenched cramp the patient cannot release. The phenomenon is called phantom limb pain, and for centuries it was simply mysterious. Doctors first described phantom limbs in detail during the American Civil War, when an army surgeon named Silas Weir Mitchell noticed how many of his amputee patients spoke about parts of themselves that were no longer present. For a long time, the suffering was dismissed as imagination or grief. We now know better. The brain holds a detailed body map in the regions called the somatosensory cortex. When a limb is gone, the map does not immediately update. The brain keeps sending and listening for signals from a place that has fallen silent. In the 1990s, a neurologist named V.S. Ramachandran came up with a deceptively simple trick. He sat patients in front of a vertical mirror, asked them to place their intact arm where the missing one would have been, and let the reflection complete the picture. Many patients, looking at what appeared to be both hands again, were able to unclench the phantom that had hurt them for years. The brain, given a visual stand-in, finally relaxed. The deeper meaning is striking. The body we feel is not simply a readout of nerves. It is a model the brain holds, and once a part of that model is built, it does not let go easily. A leg that no longer exists can still ache when the weather changes, because the place inside the brain that knew it is still listening. Ramanujan. In the early 1900s, a poor clerk named Srinivasa Ramanujan was working a tedious accounting job in the South Indian port of Madras. He had almost no formal mathematical training, no access to a major university, and a pile of cheap notebooks. In those notebooks, in cramped handwriting, he was deriving results in number theory that would not be confirmed or even understood for another century. Friends finally persuaded him to send some of his work to a famous English mathematician named G.H. Hardy at Cambridge. Hardy received pages of equations, some of which he recognized as known, some of which he could not prove either way, and some of which were so strange that, in his own words, they must be true, because no one would have the imagination to invent them. He arranged for Ramanujan to travel to Cambridge in 1914. Over the next 5 years, the two mathematicians produced a body of work that quietly transformed several branches of mathematics, from infinite series to modular forms to the partitions of numbers. Ramanujan's process was utterly his own. He described the equations as gifts from a family goddess, Namagiri, who appeared in dreams and offered him formulas. Whatever the truth of that experience, the results were astonishing. Identities he wrote down without proof have since been used in the calculation of pi, in the design of black hole physics, and in modern algorithms that run on supercomputers. He died in 1920 at the age of 32, weakened by years of poor nutrition and chronic illness. His notebooks survived. Mathematicians are still working through them. One of the last batches, the so-called Lost Notebook, was rediscovered in 1976 in a box at Trinity College and has since seeded entire careers. A clerk in a colonial port quietly handed his future colleagues a century's worth of homework. The Pirahã Language. Deep in the Amazon rainforest of Brazil lives a community of several hundred people called the Pirahã. They have lived along the banks of a tributary of the Amazon for centuries, and their language is unlike any other ever documented. For decades, missionaries and linguists tried to translate religious and historical texts into Pirahã. They kept hitting the same wall. The language does not have words for exact numbers, beyond rough notions of one, a few, and many. It has no precise words for colours. It has no tense in the past or future the way English does. It even lacks grammatical features that some linguists once considered universal to every human language. The American linguist Daniel Everett spent decades among the Pirahã, beginning as a Christian missionary trying to bring them the Bible. He stayed, learned the language, and slowly began to argue that the Pirahã language reflects something deeper about how its speakers see the world. They are intensely focused on the present, on what they have directly experienced or heard from a living witness. Stories about events from long ago or about beings no one has personally met simply do not land. Everett's later claim that Pirahã lacks recursion, the ability to embed clauses inside clauses, kicked off one of the loudest fights in modern linguistics. Some prominent theorists, including Noam Chomsky's colleagues, insisted that all human languages must have recursion. Others reviewed Everett's recordings and largely supported him. The debate continues. The Pirahã themselves, as Everett Riley notes, remain unbothered. Whatever the final verdict, the Pirahã quietly demonstrate that human language is more flexible than the textbooks always claimed. Counting, tense, color words, and grammatical recursion are not requirements of being human. They are features some languages happen to develop, and not others, depending on how those people choose to live with the world. The double-slit experiment. There is one experiment in physics that physicists and philosophers have argued about for more than a century, and the more carefully it is performed, the stranger it gets. The setup, in its modern form, is almost insultingly simple. Fire particles, one at a time, at a barrier with two narrow slits in it, and let them strike a detector on the other side. The pattern that builds up tells you whether the particles are behaving like little bullets or like ripples in a pond. When the experiment was first done with light by Thomas Young in 1801, the pattern that formed was unmistakably wave-like. Light passed through both slits. The two emerging waves interfered with each other, and stripes of bright and dark bands appeared on the screen. Decades later, with the rise of quantum mechanics, scientists tried the same trick with electrons, then atoms, then whole molecules. Every kind of matter, when sent through the slits, painted the same wave-like interference pattern, even when the particles were sent through one at a time. The truly unsettling part comes next. Place a detector at one of the slits to find out which path each particle takes, and the interference pattern collapses. The particles, knowing they are being watched, behave like ordinary little objects. Stop watching, and the pattern returns. The act of measurement reaches into the experiment and changes what reality does. Physicists have argued for 100 years about what this means. Some say the particle takes both paths until it is observed. Some say the universe quietly splits in two at every measurement. Some say there is a deeper layer of physics we have not yet found. No experiment has settled the question. The double-slit experiment is the cleanest demonstration that the universe, at the smallest scales, does not match our intuitions about how solid things ought to behave. Gödel's incompleteness theorem. Mathematicians have always wanted their subject to be perfect. The dream was that, given enough patience, every true mathematical statement could be proved from a small, agreed-upon set of starting rules, and no contradictions could ever sneak into the system. The great German mathematician David Hilbert turned this dream into a formal program in the early 20th century. He wanted to build a foundation for all of mathematics that would be complete, consistent, and free of any gaps. In 1931, a quiet 25-year-old Austrian named Kurt Gödel published two short theorems that ended that dream forever. The first incompleteness theorem proved that in any logical system, rich enough to include basic arithmetic, there will always be true statements that the system itself cannot prove. The second went deeper. A consistent system cannot prove its own consistency from within. Mathematics, at its foundations, has limits that mathematics itself cannot quite reach past. Gödel's trick was extraordinary. He found a way to encode statements about mathematics inside mathematics itself, by translating every formula into a unique whole number. Using that translation, he constructed a sentence that, in effect, says about itself, "This statement cannot be proved." If the sentence were false, the system would prove a false thing, breaking consistency. If it were true, the system would have a true statement it could not prove, breaking completeness. Either way, the dream of a perfect foundation collapsed. The result was not a defeat for mathematics. It was a discovery about its nature. There is no view from outside the system that is itself another system you can fully understand from inside. The universe of mathematical truth is larger than any single proof method can ever capture. A young man in a quiet study in Vienna showed that some questions are not just hard. They are out of reach by design. The Banach-Tarski paradox. Take a solid ball, the size of an orange, made of nothing more exotic than ordinary mathematical points. Now imagine cutting it into a small number of pieces, just 5, with no special tools and no stretching or squashing. Reassemble those 5 pieces in the right way, and you can build 2 solid balls, each the exact size of the original. No mass has been added, no matter has been created, and yet the volume has doubled out of thin air. That, in essence, is the Banach-Tarski paradox, one of the strangest provable theorems in modern mathematics. The theorem was published in 1924 by 2 Polish mathematicians, Stefan Banach and Alfred Tarski. It is not a trick or a sleight of hand. The proof follows logically from a few standard axioms, including the axiom of choice, which lets you make an infinite number of selections without specifying a rule. Use that tool to assemble strange, infinitely detailed sets of points, called non-measurable sets, and the impossible becomes deducible. The catch lies in what the pieces actually are. They are not chunks of stuff in the way a slice of cake is a chunk of cake. They are infinitely intricate scatterings of points with no well-defined volume of their own. Real matter, made of atoms, cannot be sliced this way. You cannot perform the trick in your kitchen. The paradox lives entirely inside pure mathematics, where points have no size and infinity behaves in ways the human mind is not designed for. What the result really teaches us is humility. The everyday idea of volume, the idea that cutting and rearranging cannot create more, depends on quiet assumptions about what counts as a piece. When you let mathematics push past those assumptions, a single ball can become 2 without ever leaving the realm of strict logic. Graham's number. In the early 1970s, a mathematician named Ronald Graham was working on a problem in a branch of mathematics called Ramsey theory, which studies how order quietly emerges from disorder in very large sets. As part of his proof, Graham needed an upper bound, a number guaranteed to be larger than the answer he was looking for. The bound he produced is now called Graham's number, and it is so unimaginably enormous that the universe itself does not have enough space to write it down. A regular very large number, like a googolplex, can at least be described as a 1 followed by a googol zeros. Graham's number cannot be reached that way. It is built using an operation called Knuth's up arrow notation, which generalizes addition into multiplication, multiplication into exponentiation, and then keeps going. Each new arrow stacks another tower of these operations on top of itself. Graham's number is the result of stacking these arrows, layer after layer, 64 times in a row, with each layer itself defined by the previous one. To put this into perspective, if you try to write Graham's number using only its digits, with each digit the size of a single atom, you would run out of atoms in the observable universe long before you finished. Even writing down the number of digits in the number, or the number of digits in that, fails for the same reason. The number is so large that it stops fitting into any physical universe at all. What is genuinely strange is the way mathematicians have learned to work with such a giant. They know its last few digits. They can prove statements about it, even though they cannot meaningfully write it. Graham's number sits as a kind of monument to how far human reason can reach, far past the boundaries of the world that contains it. Antimatter asymmetry. Of all the unsolved puzzles in physics, one of the strangest is that anything exists at all. The standard model of particle physics is, in most respects, beautifully symmetrical. For every particle of matter, there is a corresponding particle of antimatter, identical in mass, but opposite in charge. When a particle of matter meets its antimatter twin, the two annihilate each other in a flash of pure energy. In the earliest moments after the Big Bang, energy was streaming back and forth into pairs of particles and antiparticles in nearly equal numbers. If that symmetry had held perfectly, the early universe should have produced exactly as much matter as antimatter. As the universe cooled, every particle should have found its antipartner and annihilated cleanly. The result would have been a cosmos full of light, travelling forever, and almost no leftover atoms at all. Stars, planets, plants, and people would never have formed. Yet here we are, made of matter, surrounded by matter, with antimatter rare enough that every gram of it costs a fortune to produce. Somewhere, in some way, the original symmetry was broken. For every billion antimatter particles created in the early universe, roughly 1,000,000,001 matter particles were created. The annihilation went mostly to completion, and the tiny leftover became everything we now see, including ourselves. The leading explanations involve subtle differences in how matter and antimatter behave under certain particle interactions, a phenomenon called CP violation. Experiments have seen hints of it, but not enough to fully account for the gap. The puzzle is not just academic. It is, in a real sense, the reason for our existence. The cosmic accounting was almost balanced, but not quite, and the slight excess on the matter side was just barely enough to spare a few atoms from the Great Annihilation. The universe you see is whatever survived the missed handshake. Tabby's Star. Among the many thousands of stars catalogued by the Kepler Space Telescope, one quietly stood out. Officially designated KIC 8462852, the star is more commonly called Tabby's Star, after the astronomer Tabitha Boyajian, who first led the team investigating it. It is a fairly ordinary yellow-white star, sitting about 1,400 light-years from Earth in the constellation Cygnus. What it is doing is anything but ordinary. Most stars studied by Kepler dim ever so slightly when a planet passes in front of them, usually by a fraction of a percent. The dips are clean, periodic, and predictable. Tabby's Star does something different. Over the years Kepler watched it. The star repeatedly dimmed by enormous amounts, sometimes by more than 20% at a time, in irregular and unpredictable patterns. No known planet could cast a shadow that big. Most stars never dim by more than a fraction of a percent. For a few weeks in 2015, when the data was first published, even sober scientists wrote papers wondering aloud whether the dips could be caused by an enormous artificial structure, a so-called Dyson swarm, built by an advanced civilization to harvest the star's light. Most researchers were careful to emphasize that this was almost certainly not the case. Even so, the dimming was extreme enough that the idea reached the public, and Tabby's Star became briefly famous as the alien megastructure star. Years of follow-up observations have shifted the picture. The dips behave differently for different colors of light, which is exactly what you would expect from a cloud of dust, not from a solid structure. The current best explanation is uneven swarms of fine dust orbiting the star, possibly from the breakup of a planet or moon. The cosmos, as usual, turned out to be stranger than fiction, but in its own quietly natural way. The Boötes Void. In 1981, a young astronomer named Robert Kirshner was leading a survey to map the distribution of galaxies in a patch of sky near the constellation Boötes. Most surveys of this kind reveal a familiar pattern: galaxies clumped into clusters, clusters threaded into long filaments, and filaments wrapped around vast bubbles of mostly empty space. The team was prepared to chart yet another stretch of this cosmic foam. What they actually found was something so empty, so unexpectedly large, that the result almost seemed like a mistake. The Boötes Void, as it was named, is a roughly spherical region of space, about 330 million light-years across. Inside that staggering volume, the early surveys found almost no galaxies at all. Further work has detected a small handful, perhaps 60, scattered across the void in a thin sprawl, where a comparable volume of average space would contain thousands. The astronomer Greg Aldering reportedly remarked that if the Milky Way had been at the center of this void, we would not have known there were other galaxies until the 1960s. What makes the void so striking is not just its emptiness. Voids are a common feature of the universe, woven into the structure of the cosmic web. The Boötes Void, however, is unusually large for the local part of the universe. Current theories suggest it may be the result of several smaller voids gradually merging together as the matter in their walls collapsed inward into surrounding clusters, leaving behind an even bigger pocket of nothing. For the astronomer with a backyard telescope, the void is invisible. The stars of the constellation Boötes lie in front of it, in our own galaxy. Beyond them, however, stretches a quiet emptiness most of us never think about. The universe is mostly full, but every so often it pauses for a while and leaves a very large blank space. TON 618. If you wanted to find the most absurdly massive single object known in the universe, you would have to look toward the constellation Canes Venatici and aim for a galaxy about 10 billion light-years away. At the heart of that galaxy sits a quasar called TON 618, named after the Tonnant-Zintler catalogue where it was first noted. At its core is a supermassive black hole so vast that when astronomers measured it, they had to double-check their math several times. The black hole at the centre of TON 618 is estimated to contain roughly 40 billion times the mass of our Sun, though more recent measurements suggest it could be even larger. To put that into a more useful picture, its event horizon, the boundary beyond which nothing can escape, has a diameter many times wider than the entire orbit of Neptune around the Sun. If you set it down where our Sun is now, every planet in the solar system, along with the distant icy bodies of the Kuiper Belt, would lie deep inside its perfect dark sphere. A quasar is what astronomers call the brilliantly glowing center of a galaxy, where the supermassive black hole is actively swallowing huge amounts of gas. As that gas spirals inward, it heats up to extraordinary temperatures and shines across billions of light-years. TON 618, despite being one of the most distant objects easily studied, blazes more brightly than 100 normal galaxies combined. When you look at it through a telescope, you are looking back in time, watching the universe as it was more than 10 billion years ago, when our solar system did not yet exist. By now, that quasar has probably gone quieter. What remains, if anything, is the most massive black hole humans have ever weighed. The cosmos was apparently in a generous mood when it built that one. The Fermi Paradox. One summer afternoon in 1950, the Italian physicist Enrico Fermi was eating lunch with colleagues at Los Alamos National Laboratory. The conversation drifted to flying saucers, then to interstellar travel, then to the enormous number of stars and planets in the galaxy. Fermi listened, did some quick mental arithmetic, and then asked one of the great questions of modern science. If the galaxy is so old and so full of planets, where is everybody? The numbers behind his question are striking. Our Milky Way galaxy contains somewhere between 200 billion and 400 billion stars, with at least as many planets. Some of those planets have been around for billions of years longer than Earth. Even if intelligent life evolves on only a tiny fraction of them, even if those civilizations spread outward at a small fraction of the speed of light, a galaxy this old should have been colonized many times over by now. Probes, signals, traces of activity should be visible somewhere. We see absolutely nothing. This silence is the Fermi Paradox. Proposed answers fall into a few broad camps. Maybe intelligent life is extraordinarily rare, and we are essentially alone. Maybe technological civilizations destroy themselves quickly before they can spread far. Maybe everyone is out there, but quietly hiding, or simply not interested in contact. Or maybe we are too young, in cosmic terms, to have been noticed yet. Each answer has its own supporters and its own troubling implications. The honest current state of the evidence is that we do not know. Searches for alien radio signals, for unusual chemistry in distant atmospheres, and for technological waste heat have all turned up empty. The universe could be teeming with neighbors who simply have not arrived in our patch of sky. It could also be far quieter than its size suggests. Either possibility, when you stop to think about it, is profoundly strange. Radiotropic fungi at Chernobyl. In the years after the Chernobyl nuclear disaster of 1986, the destroyed reactor in northern Ukraine became one of the most hostile places on Earth for living things. Radiation levels inside the ruined core were high enough to kill most organisms within hours. Robots sent in to survey the chamber returned with damaged electronics and corrupted footage. The remaining workers expected to find a sterile, dead environment, slowly being entombed in concrete. Instead, they found life. Black colonies of fungus were growing in plain sight on the walls inside the reactor, in places where the radiation was so intense that nothing should have survived. Closer study revealed that several species of fungi, including Cladosporium, Sphaerospermum, and Cryptococcus neoformans, were not simply tolerating the radiation. They appeared to be actively drawn toward it, growing faster in the high radiation zones than in the quiet ones. Researchers began calling them radiotropic fungi. The key, scientists now believe, is melanin, the same pigment that darkens human skin in the sun. In these fungi, melanin appears to act almost like a solar panel for ionizing radiation, converting some of the energy of incoming particles into a usable form for the fungus. Experiments in shielded labs have shown that melanin-rich strains grow noticeably faster in the presence of low-level radiation, while their lighter-colored counterparts do not. The implications go beyond a strange story in a ruined reactor. Researchers are now investigating whether radiotropic fungi could be used to protect astronauts in deep space, where cosmic radiation is a major obstacle. A coating of the right kind of melanin-rich life might one day line the walls of a spacecraft heading to Mars. Out of the most poisoned ground in the world came a quiet hint about how to survive in space, growing patiently in the dark on top of an open wound in the Earth. The Bystander Effect. On a cold New York night in 1964, a young woman named Kitty Genovese was attacked outside her apartment building in Queens. Initial news reports claimed that 38 neighbors heard her cries and did nothing. The details of that case, it later turned out, were exaggerated. Some witnesses did call the police. Some did not hear her at all. Even so, the story struck a nerve, and it kicked off decades of psychological research into what came to be called the bystander effect. Two psychologists, John Darley and Bib Latane, designed a series of careful experiments in the late 1960s. They staged emergencies, smoke pouring into a room, a person apparently having a seizure, and varied the number of people present. The results were consistent. When a single person was present, they reacted quickly and decisively. When several people were present, each individual was slower to act, slower to even acknowledge that something was wrong. The presence of other potential helpers, paradoxically, made help less likely. The mechanism turns out to be familiar to anyone who has stood in a crowded room watching something puzzling happen. Each person glances at the others, looking for cues. If no one else is alarmed, the most polite assumption is that nothing serious is happening. Personal responsibility quietly dissolves into the group. Psychologists call it diffusion of responsibility. The more witnesses, the more responsibility there is to spread around, until each person carries almost none. Knowing about the bystander effect is itself a small antidote. People who have learned the concept are measurably more likely to break the spell and act. If you ever need help in a public place, the advice is to single someone out, point at one person, and ask them directly. The bystander effect feeds on anonymity. When the request becomes personal, the polite paralysis tends to break. The Cobra Effect. During the British colonial period in India, the city of Delhi was overrun by venomous cobras. The local government, hoping to thin their numbers, announced a tidy plan. A small bounty would be paid for every dead cobra brought in. The result, according to a popular telling of the story, was the opposite of what the planners expected. The Cobra Effect, as economists now call the broader phenomenon, has been ruining well-intentioned policies ever since. What is said to have happened in Delhi was simple. People started breeding cobras in their homes, in cages and pots, in order to kill the snakes and collect the bounty. When colonial officials realized they were paying for an entire industry of captive snakes, they cancelled the program. The breeders, now stuck with worthless cobras, released them. The city ended up with more cobras than it started with. Historians point out that the original story, told most famously by the German economist Horst Siebert, is poorly sourced and may be partly folklore. Even so, the pattern it describes is well documented elsewhere. The French colonial government in Hanoi famously paid for rat tails, and citizens responded by farming rats whose tails were cut off, but who were otherwise let go to keep breeding. Modern examples range from emissions rules that encouraged dirtier factories abroad, to fishing quotas that incentivize discarding undersized fish at sea. What unites these cases is a single quiet truth. When a complicated system is nudged by a simple rule, people respond not just to the rule's intent, but to the literal words on the page. Incentives reach into every corner. The challenge is not to outsmart the planners, only to follow what they actually asked for. The lesson, 2 centuries on, is humbling. A reward for dead cobras is not a reward for fewer cobras, and the difference quietly matters. The Peter Principle. Almost everyone has worked under a manager who seemed startlingly out of their depth. The natural assumption is that hiring went wrong somewhere along the way, or that office politics elevated the wrong person. In 1969, a Canadian educator named Lawrence Peter offered a different explanation in a small satirical book. He called it the Peter Principle. In any organization that promotes people based on their performance in their current role, employees keep being promoted until they reach a level where they are no longer competent, and there they remain. The mechanism is almost simple enough to feel unfair. If a salesperson is excellent at sales, the company rewards them with a promotion to sales manager. The new role requires different skills: planning, leading, hiring, and the former salesperson may or may not have those skills. If they do, they get promoted again, perhaps into corporate strategy. Sooner or later, they hit a level where their skills no longer fit the job. They are not bad enough to be fired, but not strong enough to be promoted any further. So they stay. Peter wrote his book as a wry joke, but later research has taken the idea seriously. A 2018 study by Labour economists analysed sales promotion records and found that the best individual salespeople were indeed promoted more often, yet were on average noticeably worse as managers than their less stellar peers. Real organizations, the data suggested, leak talent in exactly the way Peter described. The interesting question is what to do about it. Some companies now separate the path of expert specialists from the path of managers, so that excellent technicians can keep growing without being forced into supervision. Others train heavily for the next role rather than the current one. The principle does not have to be destiny, but ignoring it is a remarkably good way to fulfill it. The Dancing Plague of 1518. On a hot July morning in 1518, in the city of Strasbourg in modern France, a woman known to history only as Frau Trophäa stepped into the narrow street and began to dance. She did not stop. Within a week, more than 30 other townspeople had joined her. Within a month, the number had grown to around 400. Some danced themselves into exhaustion. Some collapsed from heatstroke or heart failure. The episode has come down to us as the Dancing Plague of 1518, and it is one of the strangest events in the historical record. City records of the time, kept by physicians, clergy, and civic officials, document the outbreak in unusual detail. The dancers did not seem joyful. They moved like people in a trance, sweating and bleeding from worn-out feet, sometimes crying out in apparent pain. Local doctors of the period concluded that the affliction was caused by hot blood. Their prescribed treatment was to encourage more dancing, on the theory that the patients had to dance the sickness out. Musicians were hired. Stages were built. The plague worsened. Modern historians have proposed several explanations. One is mass psychogenic illness, where extreme stress from famine, disease, and religious anxiety triggered a contagious episode of dissociation, spreading through a population already pushed to the edge. Another idea is ergot poisoning from rye fungus, though most scholars consider that less likely, because ergot symptoms do not really match the documented behavior. Whatever the cause, the dancing eventually ended, after pilgrimages to a shrine and weeks of intervention. What makes the Dancing Plague so striking is how well it is documented. This was not a rumour passed down in folklore. It was an event recorded by careful chroniclers, watched by entire towns, and remembered in the city archives. The mind, under enough pressure, can do remarkable things to the body, and history has the receipts. Capgras Delusion. Some patients with damage to certain regions of the brain develop a quietly unsettling conviction. They look at their spouse, their parent, their child, or sometimes their pet, and they recognize the face exactly. The features are familiar. The voice is right. The mannerisms match. Yet they feel with full certainty that the person standing in front of them is not actually that person, but an imposter. Someone is wearing the face of their loved one. The condition is called Capgras Delusion, named for the French psychiatrist Joseph Capgras, who first described it in 1923. Modern research has pieced together what may be happening in the brain. Recognizing a familiar face involves two cooperating circuits. One identifies the visual features and links them to a name. Another generates the warm, emotional surge that tells you, yes, this is the person you love. If a stroke, a head injury, or certain mental illnesses damage the connection between those circuits, the recognition still works. The emotional confirmation does not arrive. The patient sees the right face, but feels no familiarity, and the mind reaches for the only explanation that fits, that this must be a clever fake. The condition is rare, but real. It can be deeply painful for everyone involved. A spouse may find themselves suddenly accused of being a stranger by the person they have lived with for decades. In some cases, the delusion is brief and yields to treatment. In others, it becomes a stubborn feature of daily life. Patients are not lying. The mismatch between their face recognition and their emotional response is, to them, completely vivid. Capgras Delusion has changed the way neurologists think about emotion and perception. Recognition, it turns out, is not a single act, but a quiet handshake between systems. Most of us never notice the handshake until it stops happening. Cotard's delusion. In 1880, a French neurologist named Jules Cotard described a patient who calmly insisted that she had no brain, no nerves, no internal organs, and indeed, no body at all. She had simply continued to walk and talk, she said, because she could not properly die. Cotard documented other similar cases over the years in which patients lost the felt sense of their own existence, often combined with the conviction that they were already dead. The condition came to be called Cotard's delusion, and it is one of the rarest and most disorienting experiences in psychiatry. The patients are not joking, and they are not metaphorically depressed. They mean it. Some refuse to eat on the basis that a dead body has no need of food. Some report not feeling pain or hunger because in their experience, the body is simply no longer there. The condition is associated with severe depression, certain forms of psychosis, and damage to specific regions of the brain that integrate the felt sense of being alive. Modern researchers think Cotard's may be a kind of mirror image of Capgras. In Capgras, recognition without the emotional response leads to the conclusion that a familiar person is an imposter. In Cotard's, a more global loss of the emotional sense of self may lead a patient to conclude that they themselves no longer exist. The wiring that normally tells you that you are here, breathing, alive, present, has broken in some quiet way, and the only explanation the mind can find is that the answer is no. What makes the condition so striking is how treatable it sometimes turns out to be. Antidepressants, antipsychotic medication, and in some cases gentle electrical therapy can restore the sense of being alive over weeks or months. The terrible certainty quietly lifts. Patients describe waking up, slowly, into the world again, as if they had been somewhere else. Zombie ant fungus. In the rainforests of Central and South America, a quietly terrifying piece of biology plays out underfoot. An ordinary carpenter ant goes about its day, gathering food and patrolling the colony, when it inhales the microscopic spore of a fungus called Ophiocordyceps unilateralis. Within hours, the fungus has taken hold inside the ant's body. Within days, the ant is no longer in charge of itself. Researchers call the species the zombie ant fungus, and the name is technically accurate. The infection is precisely choreographed. As the fungus grows, it weaves itself through the ant's muscle fibers and chemical signaling pathways, while leaving the brain itself untouched. At a specific time of day, around solar noon, the infected ant begins to move differently. It abandons the colony, climbs a plant stem to a particular height above the forest floor, and locks its jaws onto the underside of a leaf. There it dies. The fungus then sprouts a long, thin stalk from the back of the ant's head, which releases a fresh cloud of spores onto the trail below, ready to catch the next ant. What makes the trick especially eerie is the geometry. The height the fungus chooses, around 25 centimeters above the ground, is the precise zone where temperature and humidity favor fungal growth. The leaf orientation maximizes the spread of falling spores. The hour of day matches when ant foragers are most likely to pass beneath. The fungus, despite having no brain at all, has evolved a procedure that exploits insect behavior with the precision of a surgical strike. Different species of Ophiocordyceps target different insects with different routines. In each case, the puppet host is led to a chosen spot at a chosen moment and dies in service of the next generation of fungus. Evolution, given enough time, can produce something almost indistinguishable from intention in things that do not think at all. Lake Natron. In the dry north of Tanzania, near the border with Kenya, sits a lake whose surface ripples in shades of red and orange. Lake Natron is one of the most alkaline bodies of water on Earth, fed by mineral-rich hot springs and a slow trickle of rivers that pick up sodium carbonate from the surrounding ash beds. The water can reach a pH close to that of household ammonia, and the dissolved minerals make it lethal to almost any animal that bathes in it. The lake looks, on a still afternoon, like a thin sheet of dilute lava resting in the Rift Valley. Photographs taken by the wildlife photographer Nick Brandt brought Lake Natron to wider attention in the early 2010s. He found the dried remains of birds and bats along the shoreline, their bodies coated in a chalky mineral crust and posed as if still in flight. Many of the images circulated online with claims that the lake had turned the animals to stone. The story was more dramatic than the truth, but the truth was strange enough. Animals that died near the lake had been preserved by the alkaline water and the rising sodium minerals, almost mummified rather than petrified. What makes Lake Natron especially interesting is that it is not lifeless. The same conditions that kill many animals are paradise for certain extremophile microbes, particularly cyanobacteria called spirulina. Those microbes give the lake its red color. Lesser flamingos, of all things, gather there in enormous numbers because the alkalinity keeps predators out of their nests. The flamingos eat the bacteria, drink the water, and raise their chicks in one of the most hostile lakes on Earth. Life and lethality sharing the same shoreline. Lake Natron is a quiet reminder that conditions deadly to most creatures are simply the environment that some species call home. Mutual assured destruction. By the height of the Cold War, the United States and the Soviet Union had built nuclear arsenals so large that, fully deployed, they could have ended modern civilization within an afternoon. The two governments faced a strange strategic puzzle. Neither side wanted nuclear war, yet each was deeply worried that the other might strike first. The doctrine they settled into, slowly and uncomfortably, was called mutual assured destruction, often shortened to its grimly accurate acronym, MAD. The logic ran like this. As long as each side possessed enough nuclear weapons to absorb a first strike and still retaliate with overwhelming force, neither side could rationally launch first. Any attacker, no matter how clever the strike, would face certain destruction in return. The threat of total annihilation was, paradoxically, the thing keeping the world from being annihilated. Stability rested on the credibility of the threat to do something neither side actually wanted to do. Critics pointed out the obvious problem. The doctrine only worked if everyone involved was perfectly rational, perfectly informed, and never miscalculated. Real history pressed against that assumption hard. The Cuban Missile Crisis in 1962 brought the world within hours of nuclear exchange. A computer error during a Soviet early warning shift in 1983 was caught just in time by a lone officer named Stanislav Petrov, who refused to forward what he suspected was a false alarm. The world did not end that night, but it could have. The doctrine still shapes nuclear policy today, in modified form. New countries have joined the club, weapons have grown more accurate, and new technologies have complicated the old balance. The strange comfort of the old days, that everyone was too well armed to dare, may not hold forever. It worked, more or less, for a generation. Whether it can keep working is one of the open questions of our age. Boltzmann Brain. Late in the 1800s, the Austrian physicist Ludwig Boltzmann was trying to explain why time flows in one direction. He proposed that the universe began in a state of unusually low disorder and has been slowly growing more disordered ever since. A clever critic asked an awkward follow-up. If the universe is governed by the random shuffling of particles, then over infinite time, occasional random fluctuations should produce small pockets of order, even islands of complexity, at random places and times. That insight grew into a thought experiment now called the Boltzmann Brain. Given a vast enough universe and enough time, ordinary thermodynamics suggests that brains, complete with vivid memories and the experience of looking at a sky, will occasionally form by pure chance out of swirling particles in empty space. Most of them will exist for a single moment and then fall apart. Some will have, in that moment, a fully detailed inner life, including memories of a childhood that never happened, a name that nobody else holds, and the conviction that they are real people standing in a real world. The chilling part of the argument is statistical. In some models of an eternal or vastly large universe, freak Boltzmann brains may outnumber actual conscious beings who got their experiences the ordinary way, through evolution and biology. If that is true, then the most likely sort of observer is not a person reading a chapter in a video script. It is a fleeting bubble of consciousness in deep space, briefly imagining a person reading a chapter in a video script. Modern physicists treat the Boltzmann brain not as a serious possibility, but as a warning sign. If any cosmological theory predicts that random brains should outnumber real ones, the theory is almost certainly missing something. The thought experiment serves as a quiet form of error checking, and so far we are still here. Vacuum decay. There is one possible end of the universe that physicists generally do not enjoy talking about over lunch. It is called vacuum decay, and unlike the slow heat death or the long cool drift of expansion, it is sudden, total, and silent. The idea grows out of quantum field theory and rests on a subtle question. Is the quantum vacuum that fills empty space the lowest possible energy state? Or is it simply a comfortable resting point, with an even lower state lurking somewhere just out of reach? If our vacuum is merely metastable, a kind of cosmic plateau, then somewhere in the universe, a tiny region of space might one day, by random quantum chance, slip into the true lowest energy state. A bubble would form. The bubble's interior would have slightly different laws of physics, just different enough that the kinds of atoms and chemistry that allow stars, planets, and people to exist would no longer be possible. The boundary of that bubble would expand outward at very close to the speed of light, and everything it touched would be reorganized into the new vacuum. The unsettling part is that, because the bubble's edge moves at light speed, no warning could travel ahead of it. One moment, the sky looks ordinary. The next moment, everything in your line of sight has already been replaced, and you along with it, without any chance to notice the transition. Cosmologists call this scenario the false vacuum decay. The best current measurements of the Higgs field and the top quark mass place our universe right on the edge between stability and metastability. Even if the vacuum is unstable, most calculations conclude that the expected time before a decay event would be astronomically longer than the current age of the universe. It is the kind of doom astronomers can mostly file away. The universe continues, calm and lit, for now. The self-aware universe. Wherever you are right now, take a breath and notice that something extraordinary is happening. Out of a quiet web of atoms and energy, a small piece of the universe is paying attention to itself. The cells in your body were forged in dying stars. The nerve patterns that let you follow these words evolved over billions of years from organisms that could not even sense light. Tonight, with all of that history behind it, the universe is using you to listen to a story about its own strangeness. Philosophers and physicists have long puzzled over what to make of this fact. The American physicist John Wheeler proposed an idea he called the participatory universe, in which observation is not a passive act, but somehow part of how reality settles into its final form. He never claimed the universe is conscious in the human sense. He did suggest, gently, that mind and matter may be more tangled together than the old picture allowed. Other thinkers have offered their own versions, from panpsychism to modern interpretations of quantum measurement. We have no definitive answer. We may never have one. The honest position is that consciousness, the simple fact of there being something it is like to be you, remains one of the deepest unsolved questions in science. From the inside, however, it does not feel like an academic puzzle. It feels like the most familiar thing in the world. So here at the end of this long walk, the strangest thing on the list may be the one carrying you through it. Stars older than the universe seem to be. Liquids that climb walls. Tiny creatures that solve mazes without a brain. All remarkable. And quietly, beneath all of it, a universe that has managed, through atoms and time, to learn how to notice itself. Sleep well. The rest of the strangeness can wait.